Maybe also wait for 1 minute.
1 minute.
Yeah, yeah. It's not for. Lectures. But today we have at least one extra mic. So whenever you have a question, please raise your hand and wait for the mic, and then you can ask your question. The same thing when we are discussing the papers. So in the discussion part of the paper, which is going to be one of the the exciting parts, we're going to have back and forth discussions for each paper. So make sure you you wait until you get the mic and then you talk about the points that you have. That's about this. And also, just a reminder that after today's session, I think at 6 p.m., we will release the quiz, which they are very easy to answer questions, but make sure you do it because the quiz will be only available for 1 day. So don't forget to do that. Any questions regarding the format? We have to waste more time. Maybe you can present on PDF. I don't know.
Yeah.
Has permission, I don't know.
But
Can you join the Zoom and present?
yeah, Zoom from my Mac, for example.
Yeah,
Okay.
that was.
Yeah. Yeah, you get something from there. we see it now.
So you need to stop. Sure.
It works here, right?
Oh, okay.
No, it doesn't.
Oh, the problem. That's the problem now. Oh, okay. The problem is we need to do this. Then we need to go to zone. And
It's mine, right? Yeah, it's mine. Cool. We're done.
yeah, but we need to project this page here. Maybe we are in the extended mode. I don't know. Maybe we should go to mirror.
Mirror. Change. Yeah, good. Good enough for
And
now.
then click on it.
That's good enough for now.
Yeah.
Okay. Yeah. Wait.
Sorry for this late, guys. So today's session is going to be about LLM inference. And the first presentation today is about, we're going to present the paper PIM is all you need. And the presenter is going to be Prathamesh here. So Prathamesh is a first year master's student in the Electrical Engineering and Information Technology program at DATED, having started this semester. His interests are in performance computing, and his background is in implementing optimizations at both the algorithmic level for image processing and the machine learning domains. Overall, his goal in ETH is to strengthen his fundamentals in these areas and to get exposure to cutting-edge research in related domains. So, without further ado, let's get started. This.
Yeah. If it's green, they can hear you.
Okay.
With this.
So, welcome everyone. I hope I'm audible correctly. And let's start. So, we are going to see this paper today. The title is PIM, that is Processing in Memory is All You Need. So, it's going to try to explore some ideas related to LLM inference, basically how we can make it more energy efficient as well as try to improve the performance of it, so reducing latency. So, let's first have a look at the executive summary. So this is basically a very high level, you can think of it like a 10,000 foot level summary of the paper and the ideas that it introduces. So the motivation to do all of this is to make LLM inference as much energy efficient and fast as possible. And that is why they are doing all of this research. The key problem in order to realize this goal that they have identified is the data movement bottleneck. So they have identified that if you can actually try to alleviate this data movement bottleneck, you would end up with solving quite a lot of problems. And the idea that they have introduced in the paper for solving this bottleneck is utilizing processing in memory (PIM) techniques to essentially make your computation go towards your data instead of the other way around, which is usually the case for all processor-centric architectures. So some of the key results that they have achieved are up to 4.2x energy reduction, up to 2.9x, up to 4.2x reduction in the latency, up to 2.9x energy reduction, and tokens per dollar factor is approximately reduced by 5.9x in 5.2x in many cases. So the baseline GPU system that they are going to use in all of this work is the A100 GPU system, and all of these results are in comparison with that. So let's move ahead. The paper is going to deal with many ideas. The first general idea or the first general thing that you are supposed to know in order to understand the problem and better appreciate the solution is the current bottleneck on GPUs. So I'll be providing a very quick GPU refresher. It's going to be something very quick, only about the facts that you are supposed to know to understand the problem. So let's see. So as most of you already know, that GPU is this device with many cores and multiple levels of cache hierarchy in order to support the data movement. All of this cache hierarchy is basically there to solve the data movement bottleneck, so that you do not, so you're not waiting for the data, or you are waiting as less as you can. But that ends up anyway becoming the bottleneck. So one thing that you should remember is that all of these caches are supposed to interact with many levels of cores, and all of these cores are supposed to be busy all the time in order to keep the device engaged for as long as you can. So each core has many floating point units and integer units, and all of these cores have some of the local caches. Since you want to engage all of them for as much time as you can to achieve peak hardware utilization, you want to have the data available for each and every core at all places. So you basically want to have the data that you are going to use in the cache that is closest to the core, so that you can deal with it as fast as you can. These are the two things that I want you to remember. So first thing is you want to keep all the cores busy as much as you can. And the second thing is for this to happen, you have to have the data for all the time. So you have to have all the data in the correct cache, which is closest to the core for as much long as you can. So this was basically a background related to GPUs. Let's now have a look at the algorithmic level. So here I'm going to present some of the concepts related to LLM inference, which are essentially key to understanding the problem itself. So let's have a look at how LLM inference works. So LLM inference usually has two main stages. So the first thing is the prefill stage, which is also called as prompt summarization. What you do here is that you essentially try to understand the prompt that the user has given you, and basically try to make sense of things. So you try to see how things are interconnected with each other, which other things are more important, and so on. So all of the prompt is available to you beforehand. So you can essentially just tokenize each and every word inside the prompt, and create this one in big input matrix, and do some calculations on top of it with the model weight matrix. So this is going to result into things which are being operated on two large matrices. So you are going to essentially do things like matrix multiplication or matmers on very large data. The second stage here is the decoding stage. This is the stage which comes after the prefill stage, and in this stage, you essentially, or the model essentially generates one new token every time. So it tries to generate new tokens for the output in a regressive manner, and you are basically going to process data in a serialized way, because you are going to go through all of the layers for each and every token, and all of this computation is going to look something like this. It's going to be one small vector which is related to the query. And it is being operated on the model. It is being operated on with the model weights. So this is essentially a repetitive serialized process, which is why it takes a lot of time and often becomes the timing bottleneck for LLM inference. So this is the problem that we want to solve through these ideas. So let's now try to understand the decoding stage better. You can see that the decoding stage has multiple blocks, and one of these blocks is the fully connected layer inside the transformer. You also have self-attention, and once you perform this self-attention with the KV cache, you then again feed the result to a fully connected layer for doing things related to normalization and all the other related things. So you can see that you have this KV cache in the self-attention layer. Now this is a software implemented cache where you try to store the context of all tokens which came before the current token, so that your conversation is still relevant for the user. So you essentially try to store everything that you generated already while generating things for the new token. So let's now try to understand how batching works in LLM inference. So you can see that there are multiple types of layers in the model architecture itself. So the first type of layer is definitely fully connected layer, and batching here is very straightforward. You just need to essentially create a batched input vector of multiple queries, and you can just operate on it with these model weights. Now these model weights are shared across all the queries, so you can really batch all the calculation together and end up operating on two very large matrices without having to deal with other things. So this is very straightforward, very doable. But the other kind of layer that we have in LLMs is this attention layer, which we discussed in the previous slide. So you can see that this attention layer actually operates on the query for the new token, as well as the KV cache. And this KV cache is going to be very different for each and every user query. You cannot essentially reuse this KV cache for multiple queries and then try to batch things. So it basically looks like this. You have this one output query vector and a separate KV cache for a different user query. And this goes on and on. So you cannot really batch it in a very straightforward fashion, which is why you cannot really convert this into somehow operations on two large matrices. And that actually leads to the bottleneck that we are going to see in the further slides. So let's now compare the GEMM, which is essentially what we saw in the batching of fully connected layers, and MATVEX, which is basically matrix vector multiplication, which we saw while we had a look at the KV cache. So the one key parameter in which both of this kind of computations differ is the operational intensity. So the operational intensity in MATML is quite high. It's calculated by computing the number of operations that you do divided by the amount of data that you bring in to do those calculations. The assumption here is that you are operating on 2-byte data. So the paper assumes that the input is going to be about BF16 data type, and that is 2 bytes. Similarly, for MATVEX, the calculation is exactly the same, but you can see that the operational intensity is not as high. I mean, definitely not as high as MATML. It's many orders, or it's many times lesser than the MATML itself. If you compare this with the operational intensity on the A100 GPU, you would get this number. So this number is 156, which is definitely smaller than 2000, but it is still significantly larger than 16. So what does this mean? This means that when you were doing MATMLs, that is matrix multiplication, you were essentially having a higher operational intensity, and you could do many operations on the same data that you brought in the cache hierarchy many times. So most of your cores were actually very busy. But you were doing things, when you were doing things on MATVEX, the story looks quite different, because here you are not doing as many operations as MATML on the same amount of data that you brought inside the cache hierarchy. So essentially, you are not keeping all the cores busy all the time. So can you now guess the problem on the basis of the conclusion of the first section, which was the GPU section, and on the basis of the second section, which was an algorithmic layer introduction? Can you now try to guess what the problem might be? Yes.
There's still a lot of data movement and not as much parallelization as efficient.
Exactly. That's the correct answer. So as he correctly said, that in the case of MATVEX, there is a lot of movement in the cache, but it's still not performing as many operations as it was performing in MATML. So essentially, you're not able to keep all the cores busy all the time. So yes, this is a problem. Essentially, your GPU is under low utilization, and GPU is a very expensive component in your architecture, and that is under low utilization. So this is the problem that we want to solve. And remember, you are paying actually 3-way here. So the one way that you are paying for this problem is definitely in the data movement time that you are taking in order to move things. The second thing is when this happens, you end up consuming a lot of energy. So energy is also wasted quite a bit. And the third thing is, of course, cost, because you cannot really get a very high throughput from your devices. So you end up buying more devices, and then you end up paying more. So it's really a 3-way loss. Now, this problem that we studied is for LLMs, and we understood from the algorithmic layer as well as the hardware as to why this problem really exists. But it really exists in LLMs. If you were to see the hardware utilization for other models, for example, BERT and ResNet 152, it's not as bad. I mean, sure, BERT does not have a very high utilization when compared to ResNet 152, but it's still significantly better than what you have for Llama 2 70B. So does anyone want to answer this? Can anyone think as to why this might be the case? Why are we seeing very low utilization in an LLM like Llama 2, but other two models like BERT and ResNet perform relatively better? Should I give a hint?
I want to say, don't worry about Mike. We will distribute systems.
Think about the operations, the kind of mathematical operations that are there inside these models. Think about things from the algorithmic layer. Don't be very fixated on the hardware. Think as to which operations you are doing inside BERT and ResNet 152. Okay, no problem. So if you see BERT is basically an encoder-based model. And this is not an autoregressive model where you are generating tokens one by one. It's still operating on larger matrices. And when you're operating on those sizes, your operational intensity is essentially high, which is what you want to keep your GPU streaming multiprocessor cores busy all the time. So it's actually able to do that. And for ResNet 152, the model is convolution based. Now, convolutions can be mapped to matmals using some intelligent algorithms. And there are ways to do this. Of course, you pay the cost for this mapping during the packing and tiling stage when you are executing this on your GPU. But that still benefits you because once you do that, you can essentially engage tensor cores which have very high throughput, and it still makes things good for GPU. So let's now try to formulate the problem mathematically. We had an intuitive understanding of the problem by looking at the algorithmic layer. We also saw the hardware layer as to what its requirements were, and we had this intuitive bridge in between them. Let's now try to mathematically formulate it. So you can see that the compute throughput is directly proportional to the operational intensity that you have for your computation, and it's also directly proportional to the memory bandwidth that you have for your hardware. Now, the first thing is coming from the algorithmic layer. Operational intensity is coming from the algorithmic layer, while the memory bandwidth is really coming from the hardware, the kind of hardware that you have. And since this is the case, and we are essentially using KV cache, so we are kind of fixated on using the same algorithm because that is what the math has suggested us. So we are essentially reducing the operational intensity, but we still want to keep our compute throughput at least constant, or maybe make it better if we can. Then what can we do here? What would the solution solve in this equation so that the compute throughput still remains high, but the operational intensity has reduced? So yes, the one way to do it would be to increase the memory bandwidth. If you were to increase the memory bandwidth, you would essentially offset this decrease in operational intensity and still keep the compute throughput high. So any ideas as to how you can basically reduce or how you can actually increase the memory bandwidth? Anyone wants to suggest something? And remember, I said that memory bandwidth is a feature of your hardware, the kind of things that you are using your model to run on. And operational intensity is a feature of your algorithm. Now, this is not changing, but that one can probably change. So does anyone want to guess which kind of hardware or which kind of system we are going to use so that we get higher memory bandwidth? Okay, no worries. So yes, the kind of system that we can use is essentially PIM. PIM is processing in memory. And if you were to use, if you were to do all of this processing in memory, you would get very high memory bandwidth. And that would essentially help you increase your compute throughput or maybe keep it constant, even though the operational intensity was decreased. So that is the whole intuition as to why this solution was chosen. So, okay, we have now formulated the problem and we have an intuition as to how the solution would look like. So definitely we can use PIM to improve this memory bandwidth for that part. And now we can come to the system itself. So the authors call their PIM system as CND. CND is basically CXL-Enabled no GPU system. So basically you don't have any GPUs and you have CXL-Enabled things or enabled devices connected with each other. So let's have a look at how this memory bandwidth thing looks like for both the cases, the case where you are using PIM and the normal case where you are not using the PIM. So you can see that the authors calculated that the memory bandwidth for the A100 GPU system that they were using is about 2 terabytes per second, while the bandwidth, the internal memory bandwidth for the GDDR6 PIM device, which they are going to use for running their model, is about 16 terabytes per second. So it is immediately apparent that yes, the difference in bandwidth is substantial. And if you were to use the thing with a higher memory bandwidth, you would probably get closer to the solution. Okay, that is one part. But another aspect of large language models is that they require a large memory capacity. So they really have to have something like 400 or 500 gigabytes of memory stored either in the HBM or on any other kind of storage that you are using for the model to function. Consider this example of Llama 70 billion, which has about 4K context length and batch size of 128. And you can see that it requires 140 gigabytes in model weight and 310 gigabytes of KV cache. So this is also something that we want to look out for when we are designing the solution. The first aspect is, of course, memory bandwidth, which was the missing factor, you can say, in GPU. But the second aspect for large language model inference is also this large memory capacity. So we have to have a solution which also satisfies this requirement. Now, PIM devices are in general suffering with reduced memory density. They do not have a lot of memory density. And since you cannot have very dense memory, you cannot really keep all of this memory into one monolithic structure, which has about 450 gigabytes. The form factor would just not match in order to really make it. You can see that most of the popular PIM manufacturers have a memory density which is less than 75%. And this essentially leads to you not being able to have huge amounts of memory in this one monolithic structure. So what can you do here? So this is where CXL comes in. CXL stands for Compute Express Link. And this is how the authors solve this problem. So the first problem of memory bandwidth was solved by the nature of PIM itself. And the second problem of memory density is then solved with CXL. So you can see that CXL is this technology to connect multiple devices with each other. And when you connect multiple devices like this, you can essentially pool in all of their resources. So you can use all of the memory that they have to offer. You can also use their individual processing units and map computation on them in a very clever way to extract parallelism and make things go fast. So this is basically the CENT system. It consists of multiple PIM devices kept inside a CXL device, and then you connect about 32 such CXL devices with each other in order to form this one big system. They call it CENT, to essentially solve both of these problems. Now, this system has computation units placed near the memory, so definitely it has very high memory bandwidth. And also, since you are connecting all of these devices with each other, you have very high memory capacity available as well. So you are essentially solving both of those problems. So let's have a look at the architecture in a little bit more detail. You can see that you have this one single host CPU, which is supposed to control everything. The CPU decides which thing runs on which device and how things really move in between these devices. You have this one CXL switch. The switch is responsible for coordinating the connection between these devices. So all of these devices have this two-side connection with the switch, and all of them send their requests through this switch. Now, one thing that immediately stands out to me in this CXL system is that everything is going through the switch, unlike the NVMe system, because there you can have peer-to-peer GPU connection, and really each GPU can talk to other one. But here you really have this one switch, and it is supposed to supervise every communication that you have for all of these devices. Let's now see what each of these individual devices have. So every device has three main components. So first thing is CXL controller. This part is responsible for all the communication happening in the system between devices as well as the host CPU. Then you have PNM units, and then you have GDDR6 PIM chips. The terminology related to PIM and PNM in this paper is a little bit different than what we usually do, what we usually use in class or the literature. So what they mean by PNM here is that they have some specialized math units to perform some exotic math operations, for example, exponentiation or square root or reduction, separately outside of the PIM chip. So the PIM chip has a capability to do processing, but that capability is quite limited. It can only do multiply accumulate operations, or MACs. It can only support MACs near the bank. But whenever you have to have something like exponentiation or more complex, you have to move that data from your PIM chip to the nearest PNM unit. And then that unit can do things, and then you can essentially just receive it or send it to another CXL device, depending on how it is used. So 16 such PIM chips are placed inside this device, and every device has this one PIM unit, which is supposed to take care of the computation from all of these memory modules. So let's have a look at the hierarchical computation design that we have. So first thing is PIM module. You can do simple MACs, multiply accumulate operations here. And the second thing is this PNM accelerator, which is required for more complex and exotic computations related to reductions and exponentiations and things like that. You can see that most of the computation, about 99% of this computation, can actually be just mapped to the PIM module. You don't really have to move the data from inside your GDDR6 PIM chip to the nearest PNM unit. You can just do things near the MAC unit that is there in the memory bank, and you are done with it. So that is actually a very good thing. But yes, some of the operations still require PNM. We can see this in individual blocks as well. I have considered this self-attention block for this. You can see that most of these layers are blue, have blue in majority, and that blue basically means that they can do things on the PIM module itself. Only some things like scaling or RMS norm have things which are needed to be mapped on PNM. Now normalization has two reductions. So one reduction is mean calculation, and second one is variance calculation. So both of those reductions are to be mapped, but all the other things are mostly MSEs, and they can be just done inside the PIM module itself. Similar is the case with the feed-forward network. Most of these things can be just done inside the PIM module, and you essentially don't pay the cost for data movement, even from PIM module to the PNM unit. Let's now see each of these units in more detail. So the PIM channel has these units placed near the memory bank inside each chip, and all of these units are connected with the global bus from the global buffer, as well as with the local bus from the bank. So you can essentially move your data from one device, from one CXL device to another CXL device, and then use that second device's MAC unit to calculate things. So in this case, your data will be moved from the global bus, and it will be fed to this MAC device of the second CXL unit, and then you can essentially calculate or access the local data from the local bus and perform calculations on that. The second processing device that we have is this PNM unit. This one is for more complicated math operations. So it supports reduction trees, exponentiations, and things like that. It has Taylor series coefficients stored up to index 32, and it can just multiply all of those coefficients and accumulate correctly to calculate the result of the exponent operation. Now, each PNM unit has 32 lanes. Now, remember, as I mentioned, that each PNM unit is essentially shared between 16 GDDR6 PIM channels. So 16 GDDR6 PIM modules, and each of these modules has 2 channels. So you essentially end up with 32 channels, and all of those 32 channels are one-to-one mapped to these 32 lanes inside the PNM unit. And the PNM unit can deal with data that is coming from all of these individual chips simultaneously. So you end up having like 16x parallelism, and you can have 256-bit data access from inside of these chips inside the PNM unit. Let's now have a look at some of the basic primitives that they have already implemented. So these primitives are implemented in the form of instruction sets, and they are implemented in the device itself. So the compiler or the code generator does not really have to care about this. It can just emit these instructions, and then the CXL switch will basically take care of all of this communication. So the first thing that we are going to see in this is this multicast primitive. Now, multicast is very much similar to broadcast. Essentially, you are just copying things from a small number of devices to a large number of devices. So most of the devices will receive, and only some of these devices will be essentially sharing the data for this casting. And this is implemented as an instruction. So the compiler or the programmer does not have to worry about how each of these individual devices will interact with each other. All of those calculations and that mapping of communication will be done via the CXL switch itself. The second thing that they have is this gather instruction. Now, gather is basically getting data from all of these devices, from multiple devices into a less number of devices. So you are essentially getting all the results of your computation, and you are just trying to store them into this one single place, or maybe 2 places, and then you are trying to move ahead with the execution. This is essentially used in distributed computing, because if you are distributing your calculations to multiple places, you want to have some way to essentially just relay back all of these results, and you can use those results any way you want later. Okay, so we have had a look at how the individual operations are performed inside the CENT system. We have had a look at how the algorithmic layer works, and we also had a mathematical understanding of the solution itself as to why that works. It solves both the memory bandwidth as well as the memory density problems. So let's now finally have a look at how we can bridge the algorithmic layer with the execution layer. We need to map computation from the algorithmic layer on the execution layer so that you can actually use it to calculate things. And that mapping can be done in two ways. So you're essentially mapping parallelism from your model on the device so that you can run it fast. So the first kind of mapping that they have in the CENT system is pipeline parallel mapping. And you can see that essentially you are dealing with multiple pipelines or multiple queries in parallel. So this should just increase your throughput. And you can see that each CXL device is processing the same transformer block or the same model block for multiple queries in a concurrent way. So all of this can lead to a better throughput when you have multiple queries to process. And each query processing time is not very different from, let's say, the second query's processing time. The second kind of mapping that you have here is this tensor parallel mapping. This is essentially useful when you don't have multiple queries to deal with and you want to distribute your computation from one query onto multiple devices. This can actually help, for example, when you have a very high context length and you have to generate a very long response. In those cases, maybe you can try to distribute some of the independent pieces of computation after doing dependence analysis on different parts of this system. And then you can essentially just combine all of these results. You can see that this thing really requires those primitives that we discussed, this multicast and gather, because multicast will help you distribute that computation, while gather will help you receive that computation at the right place. So this was the system's overview as to how it works and which different components it has. Do you guys have any questions? Okay, if we don't have any questions, then I'll move ahead. Let's have a look at evaluation, basically the evaluation bench. So the authors used 32 CXL devices in comparison with 4 NVIDIA A100 GPUs. The GPUs have a memory of about 320 gigabytes, and CENT system has memory of about 512 gigabytes. Now, keep in mind that this is essentially higher, so you are getting higher memory when compared to the GPU, but the cost is still very low. If you see the total cost of ownership, it's less than less by a factor of about 2.4 times. So you end up getting more memory with less cost. Now that is very good, because usually a very expensive component when you are dealing with these kind of specialized accelerators is the memory itself, because you require a lot of it. And in this case, even though you have more memory, you end up spending less. So if your model can fit on an NVIDIA GPU, if it can fit in 320 gigabytes of HBM, it can fit in on the CENT device as well, and you still have more memory. So you can essentially map more computation, maybe things like pre-processing or post-processing. That is one advantage. They also have a better bandwidth as compared to the GPU, and that is expected. I mean, that is the whole reason as to why we use this solution. Do note that the compute throughput for the CENT system is significantly lower than the GPU system. You can see that the compute throughput here is less than 2 times of what the GPU has to offer. But even so, we end up performing better. So essentially, an increase in compute throughput is not what was really required in order to reduce the wall clock time. Let's now have a look at the conclusion. So the paper establishes that LLMs have low operational intensity due to the kind of computation they have in the algorithmic layer. We have had a look at all of those things, and we saw that essentially you have things like MATWIC, which have low arithmetic intensity. The second thing that they proposed is the solution. So the solution's characteristics, we had a look at some of the desirable characteristics that you would have in your solution. And the first one among them was that you should have better memory bandwidth. So that was established. Then we also had a look at the second part of the problem, or the second part of the characteristics required for your solution. And that was that you should be able to support high memory capacity. So the authors solved that problem for usual PIM systems using the CXL interconnect technology. Then after that, we had a look at how this computation was performed inside the CXL devices. We saw that we have hybrid computational units to do a different kind of computations so that we don't end up paying a lot and can still support more and more operations. And finally, we also had a look at some of the primitives that they have already implemented to support parallelism mapping from the algorithmic layer to the execution layer. So we had a look at two of these primitives. They also have more primitives, but for the sake of brevity, I'm basically going over the most important two that I think are most important. Okay, so this is again the executive summary that I presented in the beginning. We started with the motivation as to why do any of this. Then we had a look at the problem itself. Before looking at the problem, we also had a very quick refresher of some of the related concepts in case someone needs a refresher. Then we formulated the problem mathematically and tried to have an intuitive understanding of the solution. We thought the characteristics that an ideal solution would have in these cases. Then we saw how the authors actually achieved those characteristics and solved the problems that were encountered while doing so. So we had a look at the idea, and then finally we saw the results. And with all of this, you can get a latency reduction factor of up to 4.2 times, energy reduction up to 2.9, and of course increased token per dollar up to 5.2x when you compare it with the baseline A100 GPU system. So let's have a look at some of the strengths of the paper. So yes, the first strength is the authors are considering performance, energy, and cost from the get-go. Now, this is something that was not done by the previous systems, which is why we have this huge data movement bottleneck in the first place. But these guys are really just considering all of it, and they are seeing a more global picture from the start. Now, having a look at things from a more evolved or global perspective helps, because then you can really take decisions based on the end-to-end overall performance. Like you don't try to do things which will improve the performance in a local fashion, but then keep other like adversely impact other things. You can just balance those trade-offs together and see end to end. So that is one good thing in my opinion. Then the second strength is that the system itself is quite flexible. They are talking about LLM inference in the paper, but at no point have they specifically specialized their hardware for it. I see no reason for it to be not able to run other things which have low operational intensity. For example, depth-wise convolutions. Like it's also a kind of computation which suffers from similar problems and also has a data movement bottleneck. Maybe the system can be adapted to do it, but perhaps after doing some modifications in the software layer. Then the third strength that I think is very good is that they have open sourced their software. Not all projects do this. So this is actually very good because people can just verify things and also try to understand things better from the device, from the code base. I have attached the code base link on the first slide. So if anyone wants to have a look at it, they can just follow that link. And finally, I think they explore ideas, some of these ideas related to interconnects in memory processing and parallelism mapping in a very good detail. So these ideas were explored in sufficient detail, and they also mentioned some of the intuition as to how they came up with those things. So let's move ahead and have a look at some of the weaknesses or maybe potential points of improvement for the paper. The first potential improvement point that I think for the paper is that they have not dissected the performance sufficiently. They have basically presented end-to-end results, but they have not compared layer by layer or operation by operation performance. This can be actually very beneficial in some cases because, for example, let's say you are very slow in layer N, but you are very fast in layer M. So end-to-end, you still have a very positive effect, and you would think that your system is doing well, but you have not caught the reason behind why you are slow in layer N. And if you can actually get that reason, you can get more insight, and that could potentially improve the system overall. So I think that usually helps almost in all cases and should have been done here. The second weakness that I think is that they have mentioned things related to BF16 data type when mentioning details about the hardware. So they have not mentioned any other data type. Now it's a very common expectation from the hardware to be able to perform computations on multiple different precision types. And the research in this direction is usually going towards even lower bits. So more active pieces of research are now trying to explore doing things in 4 bits. DeepSeek did these things in 8 bits, and it was quite impressive. And I think DeepSeek was like 6 months ago or more. So people are really trying to push this even further, even beyond with 4 bits, and maybe less for more constrained environments. So the authors should have presented these ideas, or maybe they should have at least kept their system flexible enough, or they should have at least added added support for F16 and F32. F16 and F32 are very common knowledge, and having at least an extension with that would have given it a better point for for being able to handle diverse precision types. The third weakness that I think is the programming model is not sufficiently explored in detail. They have not mentioned things as to how their compiler works in a lot of detail, and these things are often quite important. There is a lot of performance potential in how you apply these optimizations, and if they would have mentioned it in detail, then the reader would be more sure about the fact that they have extracted maximal performance at least from this layer. So maybe they could have mentioned as to how they are mapping things on individual devices, and how they are pipelining things, how many phases of pipelining they have, things like that. That can actually help. Also, if they have considered fusion for some of the optimizations or not. So maybe those details could have helped the reader to understand the level of maturity that their software stack has. The next weakness is that the system suffers from low throughput in the prefill stage. Now this can cause problems when you have a very huge query to feed to your LLM. For example, if you ask your LLM to analyze a database, then in those cases you are going to be very slow, since the system is not very fast in those things, and that can be a significant bottleneck depending on your application. So maybe they could have addressed this, or at least added some future work related directions in this for this point at least. And finally, this is related to the writing. The PIM terminology that they have in this paper is a little bit different than what we usually discuss with in class. Like we have a PIM, PUM, and PNM. But the PIM, so in our terminology, PIM essentially is a superset of both PUM and PNM. But in this case, PIM is just a different kind of memory chip. So it's a little bit different from the usual literature, and that was not immediately apparent to me when I was reading it. So I was like confused at some point. Then eventually I figured it out. So it would have been better if this was very clear from the beginning itself. Okay, so that marks the end of at least the presentation related to the paper. Please feel free to ask any questions that you might have. Does anyone has any questions? Yes.
Yeah, and strengths page, you mentioned that this was pretty agnostic to multiple applications, not only LLMs, but they had to specify some PIM and some PNM operations, right? So we might have some other chips that can perform some other operations. So we still might, for another application, need to buy other hardware, right?
Okay. So basically, the operations that they have specified for the PIM and PNM units are quite general. You essentially, for at least for machine learning, those operations is what you really need. You don't require many other things. But to answer your question better, they also have the RISC-V chip on the PNM device. So you can essentially use that chip to do more complex things for you whenever you require. You see, they have RISC-V cores. So you can essentially use those things for more complicated things, but you usually do not require more complexity. It's a very good subset of operations that they have. Does that answer your question? Anyone has any other question? Should I move ahead? Okay. Okay, so let's now move to the discussion part. I mean, you can ask questions related to the paper even during the discussion part or after this session. So no worries. Let's have a look at the first discussion point. So how would you actually optimize this problem for a processor-centric device? For example, GPU. I'll give a little bit background. So when I was applying to ETH, I attached one research idea because it was like asked in the application for me to do so. And in that idea, coincidentally, I identified this exact same problem. Although the way I encountered this is a little bit different. I did not went through the algorithmic layer. I actually just benchmarked the Llama 3.2 1 billion model. I mean, this was almost 1 year ago, and at that point, Llama 3.2 was the latest model. So I benchmarked this at that time, and I understood that essentially most of the computation on an NVIDIA A100 GPU is being spent in this MATMAC-like computation. I mean, you can read those Cutlass kernel names. It's a standard terminology. You can just find it in the Cutlass documentation. And that is how I identified this problem. At that time, I was more introduced to processor-centric architectures, which is why I proposed a solution to solve this. But we can actually discuss this here as well. This is a comparison as to how KV cache attention is different from the vanilla attention, because this vanilla attention does not have a problem. It is actually very optimal on the GPU architecture because of things like flash attention, which is a technique to fuse it. But KV cache attention is not that much optimal. So this is just a comparison as to how both of them differ. Does anyone has any idea as to how you can essentially optimize this for a processor-centric device? Okay, I will go ahead and then present my ideas.
Maybe you can explain what you mean by optimizing the problem. I don't get the question.
Okay, yeah, so this is directly like screenshots from the proposal that I wrote at that time. And yes, what I meant is trying to improve the wall clock time of the operator itself. So somehow try to improve the end-to-end time that you would see in KV cache attention operator. So that is what I meant with that. Yeah, any ideas as to how you can do this on a processor-centric device? Probably think from the perspective of data movement. Like think from the perspective of what really harms you the most. When you have a processor-centric device, what really harms you the most? Okay, I will move ahead. So essentially, when you have a processor-centric device, what really harms you the most is the data movement itself. If you can try to, find more ways to decrease this data movement and try to spend more time in the processing part itself, you would do savings in both energy, of course, because you are not spending precious energy to move things, and you would also save time because computation is many orders of magnitude faster than fetching data. So you would have peak hardware utilization. So thinking from that perspective, do you think we can try to fuse things? Okay, does anyone do you guys have background for fusion? Okay, I will give you a very short gist. So fusion is essentially combining two different mathematical operators into this one single thing, so that you just read the data once, do both of those operations simultaneously, and then just store it. In a layman's example, I would say, like, let's say you have task 1, which requires you to do 5 steps, and you have task 2, which requires you to do 7 steps. But the catch is that task 1 and task 2 share 5 steps among them. So if you can just fuse task 1 and task 2, you can start things. You can do those common shared 5 steps, and then you can just do 2 extra steps for task 2, and then you are done with 7 steps instead of the 12 steps that you would do otherwise. So that is what fusion is. So my idea in this was to essentially do more fusion in these operators. so that you can read the data only once and process it as much as you want, and then just write it only once. And I was trying to fuse the attention layer and another adjacent layer that you have in the model itself. Now, I will give a short background on the attention layer fusion itself. So you can see that attention is this formula. Vanilla attention is that softmax of qk transpose divided by root over of dk to p. Now q, k, and v. So I have written all of these legends here, and you can see that if you can somehow fuse all of those operators, you would have this one single kernel. Else you would basically, let's say, first calculate the matrix multiplication qk transpose, then you would calculate the division of it with this root over of dk value. Now all of these are huge tensors, so moving them is of course very expensive. Then you would apply the softmax. Now softmax has its own formula and it involves exponentiation. So you would do this and then again write things in the HBM, then you would again bring it back and then do a matrix multiplication with the v vector. So all of this is very, very expensive and requires a lot of data movement that you would essentially not want to have. So what people proposed in flash attention is that they propose that we can fuse all of this, all of these different operations into this one single kernel and just get done with it. So that is how they were able to save things, because they reduced the data movement drastically. And the central idea behind being able to fuse all of that was the fusion of two reductions. So basically, attention has two reductions. First one of them is the max reduction, and the second one of them is the average reduction. And if you can essentially just fuse both of these different kinds of reductions, you can then fuse all the other things which are just pointwise and matrix multiplication. So that part is pretty much straightforward. And the insight to fuse those two reductions came from this paper. This is a very famous paper from NVIDIA, which first proposed this. And then Flash Attention's authors essentially incorporated this idea with ideas related to tiling and pipelining and tensor core mapping for the whole attention operator. Like this paper fused the softmax, and then they figured out ways to fuse this already fused computation with some of the other layers. But how can we do this for our case? Like in our case, we already have this fused thing in the model implementation, but that is still not giving us very high performance results, because even after fusion, the operational intensity is very less. So we want to find ways to increase this operational intensity so that our GPU can do things better. So we can potentially fuse another layer into this already fused attention. Now, if you see this attention placement in the block, the next layer that you have is addition and normalization. And addition is a pretty much straightforward pointwise computation. You can easily just mix it. But normalization has two more reductions. Normalization has one reduction, which is the average, and the second reduction is this variance calculation. I have written these formulas, and both of these reductions, it's very difficult to fuse them. They are not fusible in a natural way. So what I proposed at that time, like almost 1 year ago, was to use insights from the paper, which I presented earlier, online softmax calculation paper, to fuse these two different kinds of reduction, and then fuse the main attention block with that block. So in that way, you would essentially, just have one single block for this whole layer. You would just have this one block for multi-end attention and addition and normalization, and then you will be done with it. So at this point, you are essentially reading data here, processing it inside this block, then writing it, then again reading data for addition and normalization, then again writing it. So you have this basically round trip to the HBM. But if you could just fuse it, then you would not have that round trip, and you would do more operations inside that one single block. That would increase the operational intensity. So yes, that was the idea, fusing both reductions in the normalization and then fusing that kernel with the fused attention kernel, which we already had earlier. So this is the first discussion point that we had. And yeah, so the second discussion point is related to one of the weaknesses in the paper. And as I mentioned, that one weakness in the paper is that it cannot provide very good throughput in the prefill stage. So do you have any ideas as to how you can try to solve that? Okay, yes.
speculative decoding help over here because you are using a smaller model first, and then you have a larger model for parallelized verification of the output? Can that can help with
No, you don't have two different models, right? You have this one single model, and you have two different stages in it. So the first stage is pre-fill stage, and the second stage is decoding stage.
No, but in speculative decoding, normally you use two models where one is a smaller one and the other is the actual bigger one. So the smaller model will have faster speed. It will be more faster because it has less. The size is less, and that will complete the pre-fill stage faster, and then you can verify all the tokens that have been generated parallelly using a larger model.
No, but the problem is not related to the model, it's more related to the hardware bandwidth. Like the model is not, the algorithmic layer is not the problem here. The problem is that you cannot really do computations in a very efficient way on the PIM system.
Okay.
So the problem is related to hardware, not to the model itself. Yes. Anyone has any other ideas as to how they can make changes in the send system so that it can deal with this? Okay, then I will present what I had in mind.
So to be fair, speculative decoding does help to an extent. It's an algorithm contribution. But as you said, it does not fundamentally alleviate the problem by itself. It just makes it that you can tolerate more of it by generating more tokens. So yeah, you both are right. Just wanted to say this.
Okay, we can have a discussion.
Yeah.
Maybe I don't understand it. Okay, I will just present what I had in my mind initially. So what do you think about placing tensor cores in the PNM unit? Like you already have this one unit for exotic calculations, and the prefill stage involves things like matrix multiplication, as we saw earlier, and you are not able to do those things in a very good fashion. But you know that tensor cores are these specialized hardware units which can essentially do this at a much faster pace. So what do you think about placing them inside the PNM unit? And what do you think about the constraints? Like which are the factors that you would probably have to consider with tensor cores on the PNM chip?
I think tensor cores only support in-date computation, as far as I can recall.
No, actually, tensor cores support FP16, FP32 mixed precision computation. So the input is FP16, but accumulation is an F32. That's the common way. int8 is this new type of tensor cores that you have in the Blackwell architecture. But if you see Ampere or even before that, I think from Volta, it was introduced in 2008, if I'm not wrong. And from then, it's FP16, FP32 accumulation.
So then, do the current GPUs, the most recent line, they also have tensor cores that support other forms, or they only have no data?
No, they have them. They have backward compatibility. They can deal with FP16 and BF16.
Okay.
So some of the constraints that we would have to think about in these cases, in this case, which is basically placing the tensor core on the PNM unit, is the form factor optimal for density, because we were keeping less PNM units and more PIM units to have more dense memory. Now, if we were to keep an extra thing like tensor core on top of it, is it still optimal for the density problem? Because we don't want to, we don't want to invalidate that solution that we already had. We also need to think about the power consumption itself, whether it makes sense to do it from the energy point of view. And then finally, we also have to look at the packing thing. Like tensor cores require the input to be in a matrix format. And for that, you have to have specialized packing in the software. And that has its own overheads. So we need to think whether the overhead that we will be having due to the specialized packing is basically worth it, given that we have a higher throughput hardware component. This was the final discussion point. These are the references, and yeah, I think this marks the end of my presentation. Please feel free to ask any questions that you might have, and we can always discuss this after the session. Thank you. Finally, I would also like to thank Andreas and Susanna. They helped me prepare the talk and they gave a lot of very useful comments. So it was really because of them. So thank you guys.
Do you have some quick thoughts?
I like this paper in general, I have to say. I don't like the fact that they are just using PIM, which might annoy some people in this room because we're more memory-centric here. But like one weakness that we were mentioning is that the lack of computational throughput inside the school devices and how it makes some things more difficult. For example, the prefix stage of LLM inference is going to take longer because that's always compute bound. And also another weakness that it creates is that you cannot perform any sort of batching because it's very limited to multi-vector operations inside of the unit. So maybe it would be a good idea to explore this further to try to alleviate some of these problems. And yeah, like we should not just be memory-centric, but try in order to like make processing memory fundamentally viable, we have to also take these considerations into account. So I think Prathamesh gave a great presentation.
That's actually a very nice introduction to the next paper.
Yeah, because it's a hybrid inference, right?
Yes.
Yeah, that's the other approach.
Okay, perfect. Thank you. Okay.
You can use this, right?
Yeah, that's fine.
Maybe
You could go.
I wanted one of you introduce in the meantime until we.
Ah,
But
okay.
okay, no, fine.
Maybe you can introduce. I can just forward you the.
It's okay. Where's your slice? Here's the
Wait, I will. Okay, I sent you the. Maybe you can do it from my phone also. Or I can do it. You can.
Oh, sorry, what's his name?
Okay, I think you can open this. I think this is not the seminar.
Oh, this is not seminar.
Yeah.
This is not seminar.
No, it's not.
Hi everyone. So Aniket is our next presenter. Aniket is a second year master's student at ETH. He completed his bachelor's from IIT Madras in India, where he also worked in the reconfigurable intelligent systems engineering lab. So today he will be presenting a hybrid LLM paper, we can say, whose title is PAPI, Exploiting Dynamic Parallelism and Large Language Model Decoding with a Processing in Memory-Enabled Computing System. So, go ahead.
No, it's okay.
Yeah.
Why? This one? Yeah.
Oh, but that might be because of the font. Because it shows that, no? I think no, it's not there. Okay, put this on. Yeah.
Yeah.
I think that's because of the font.
One
Yeah.
maybe. No,
I think if you share. Oh no, right.
no, nothing is coming here from the laptop. And this is paused.
Yes.
You could just restart it and try. You should just restart.
Is there another HDMI?
Yeah.
The HTML is broken. Oh, okay.
Should we try that?
Now what? It's not detected.
Projector is not on. Is it?
HDMI. No, there should be first one green, small green, and then you can select. For some reason, this is not. Maybe this is the broken one.
This was a
Oh, this one is fine.
Which one?
Oh.
Choose the condition.
Am I audible? I presume I am audible. Okay. Hi everyone, I'm Aniket. I'll be presenting this paper on exploiting dynamic parallelism. It's a way to use heterogeneous architectures to accelerate LLM inference. So let me start with my presentation. So a quick overview of what we'll be doing is what the paper is about. So the authors make an important observation here. Sorry, yeah.
Just a second. This is going to be presented. Not able to change it.
Do you want to just that's a problem?
Just a second.
Which screenshot something?
Yeah, I'm not able to use it. So I should close this view.
Check whether it is okay now. Sorry.
So yes, I'll be presenting this paper. Let us start with the executive summary, just to get a big picture. So first, we will be looking at one important observation that the authors make, namely that during LLM inference, different segments need different computational and memory requirements. After making this observation, the authors identify some shortcomings in existing systems. Two main shortcomings, namely that the first one that they all use static scheduling, although these segments need dynamically varying memory and compute requirements. And also they have a one-size-fits-all approach. Even though they use heterogeneous architecture, it can be made better. Then we will look at the solution proposed by this paper, how it solves both of these issues. And finally, we will look at the results, that how well PAPI performs better than existing solutions. So let's begin with the overview. So we'll be going over the background, then some motivation for what dynamic variability means and why it arises. And then we will look at what PAPI actually does to solve this, and then we will have the results and discussion. So some background, as the previous speaker also covered. I'll maybe quickly go over this. So when you have LLM inference, you essentially have an input prompt, and this is a list of tokens that is processed by the LLM, and you want some sort of output list of tokens. This actually happens in two stages. So that's first the prefill stage, and then the decode stage. So first, what happens in the prefill stage is that all the tokens of your input prompt are processed in parallel. There are some matrix multiplications that happen, and we get the first output token. This first output token is fed again to the LLM. Then we begin the decode stage. So in the decode stage, this first output token we got from the prefill is fed to the LLM, and it generates the next token. And this is again taken back, and it generates the next token. And this is called auto-regression. It happens recursively. And this is how these are the two stages in LLM inference, prefill and decode. So in prefill, you have a highly parallelizable computation. So you're multiplying all the token matrices with the keys and values. So this is highly parallelizable, but we see that decode is sequential. So since since these are parallelizable, the limiting factor here would be how fast we're able to compute the data. But since decode is serial, the limiting factor here is how fast we're able to move the data. So we call like the first sort of segment compute bound, and this memory bound. And it turns out it is in fact the decode stage that takes up most of the inference time. In GPT-3, for example, it's around 96%. So this is really what we need to be. This is what we're interested in optimizing the most. So there are ways to parallelize decode. We saw that decode was serial, which pose this problem. So there are two main ways in which decode is parallelized. These are called request level parallelism and token level parallelism. We will be looking at each in more detail. So what happens in request level parallelism is when we have multiple users give different requests, we can parallelize tokens from different requests. And so we will be feeding input tokens from multiple different requests, and we will also get the output tokens from for those different requests. While in token level parallelism, we use we focus only on the same request. So what we end up doing is we feed two tokens in and we get two tokens out. This is the way this works is we have a draft model, which is a smaller model which quickly predicts which speculatively predicts some of the tokens, and we use that as input. And if the larger LLM verifies that, we accept those inputs and we go forward. So these are the two types of parallelism possible or parallelism that is done and to make decode better. So this increases hardware utilization and also we get high throughput. So let us see what prior works have done after identifying these sort of two kinds of boundedness. So for example, if you look in detail at what happens in a decoder, we see that it has 4 stages, and it has been identified that 3 of these stages are usually compute bound, and 1 stage, the multi-head attention stage, is memory bound. So this is what has been found out in this attack paper. So in fact, it turns out that the 3 layers that were compute bound are fully connected layers, and the attention is a regressive layer. So the way they have implemented this using a heterogeneous architecture is that they simply, whenever they see a fully connected layer, they schedule it to a GPU, which specializes in which specializes in executing efficiently compute-bounded kernels. While if they see the attention layers, they send it to a processing-in-memory, which specializes in memory-bound kernels. But it turns out this is not always the case that fully connected layers are necessarily compute-bound. There are cases where they become memory-bound, and they would be better executed in a PIM. So this sort of static scheduler is not necessarily the best idea. What we really want to do is whenever we want to we will also see that the fully connected layers can dynamically vary between being compute bounded or memory bounded. So what we really want to do is whenever we see a fully connected layer, identify what its boundedness is and schedule it appropriately. And also the existing models, we see that we have only one processing in memory catered for the attention kernel. But if we are able to also, if sometimes the fully connected layer is also memory bounded, then that would also work better in a PIM, and we would likely need a different kind of PIM for that, which is not existing in the present models. So that was some background. And okay, so any questions so far? Okay, so let's move on to the motivation. So we saw that these kernels they could change dynamically. These fully connected kernels could change dynamically between memory bounded and compute bounded. We will see why that is happening. So if you consider request level parallelism, there are several reasons why you would want to change the batch size, the number of different user requests, whose tokens you are feeding into the kernel. For example, if you have a too large a batch size, of course you will get better throughput, but the latency of individual requests worsens. Maybe if you have too large a batch size, your architecture is not able to handle so much memory, does not have the capacity. Or maybe if you have infrequent requests, sometimes it is better to use different batch sizes. So these are all reasons for which you would want to change batch size dynamically during runtime. Similarly, similarly, you will also have something called mixed continuous batching. Based on the available resources, you would also want to change batch size during runtime. Also, in speculative decoding in token level parallelism, you also would want to change the speculation lengths, how many tokens you want to speculate on using the small draft model. And it is shown in this paper that changing it can give better performance. And also you would want to co-optimize this with how you change batch size before. So these are reasons for which you change the parallelism in the request level and token level parallelisms. Now, the authors of the present paper, PAPI, have done this analysis on what happens to different kinds of kernels, namely the fully connected kernels and the attention kernels, if we change the parallelism. So on the left, you see for a given speculation length, how changing the request level parallelism, that is changing the batch size, affects performance. So we see that beyond a certain point, if we, the darker dots here show more parallelism. So you see that beyond a certain point, even if you increase parallelism, your performance isn't really increasing as much. So that means that these kernels beyond this, so on the x-axis you have the arithmetic intensity, which we will see what exactly it means. It is essentially how complex a kernel is to compute. But we see that as a kernel becomes more and more complex, we see from this roof line analysis that there's a point beyond which the kernel, for the fully connected kernels, become actually compute bound rather than being memory bound. And we see that attention kernels are always memory bound, regardless of what parallelism we use. And similarly, also for the token level parallelism, we have a very similar roof line plot, and there's a cutoff beyond which only the fully connected kernels become compute bound rather than memory bound. And we also see that they require different arithmetic intensity, so maybe they need different kinds of processors for optimal performance. So the boundedness of, this is what we saw, the boundedness of fully connected layers changes during runtime based on the parallelism. So what we really need is a dynamic scheduler in place of the static scheduler present in existing architectures. And we also want to, we would like to have two different kinds of PIMs, one specialized for the attention kernels and one specialized for the fully connected kernels when they are memory bound. So it would be best to have two different kinds. And that is essentially what PAPI attempts to do. So we will move on to PAPI's architecture. So any questions so far? Yes.
Is the speculative decoding mechanism limited to the decoding stage, or can it be somehow used in the paper stage? Can you really
No, just doesn't have to charge.
So my question was: is the speculative decoding mechanism really only applicable in the decoding stage, or is there some way to actually use it in the prefill stages?
Not sure if there's a way to use it in the prefill stage, but since the prefill stage is anyway not taking as much of the total inference time, I presume it is only useful to have it really in the decode stage, because we have 96% of the total inference time in decode, and that is what we really want to optimize. So, okay, so we can move on to PAPI's architecture, I presume. Yep. So here we see, it's maybe a complex picture, but importantly, we see that we have the host CPU. We have some PIMs. We have two different types of PIMs. The ones in blue are optimized for the attention kernel. The one in red is optimized for the fully connected kernel. And we have a bunch of processing units also for the fully connected kernel in the purple box. So, and we have a scheduler. So what we want to do is the host CPU will be, of course, controlling everything, and the scheduler will dynamically allocate the fully connected kernels either to the fully connected, the PIM optimized for FC, or to the processing units. And of course, the attention kernels will always go to the attention PIMs. Yeah, so we have one, it is essentially what it is said. Yeah. So we see that we have fine-grained heterogeneity. We have three different kinds of processors here, one for two different kinds of PIMs itself, and a set of GPUs, the processing units. So how do we actually go about designing these PIMs? So for the first concern that the authors took into account was energy considerations. DRAM. So these are three different components that majorly affect energy consumption in PIMs, and they found out that most of the energy is consumed by DRAM accesses. So ideally, what we would want to do is fetch data from DRAM once and use it for multiple computations. With this in mind, we want to enable data reuse as much as possible. Yeah, so this is the split before in existing architectures and after implementing PAPI. So how they went about doing this was they analyzed the power consumption versus data reuse level. That is how many lines of DRAM are used per computation. And they had a power budget, and they analyzed different configurations of the PIM DRAM. So what you see here for P1B means you have 4 processors, 4 FPUs per 1 bank of the DRAM. And we see that, yes, and they decided that the 4P1B configuration would be ideal for the fully connected PIM because you want most parallelization. Since you want the fully connected layers have more, they have more compute, and you need more parallelization, more processing power. And 4P1B also fit within the power budget, so that is why this was chosen. Yeah, and as you can see, if the reuse level is more than 4, the power budget is satisfied. And for the attention PIM, it does not need as much compute as the fully connected layers. So 1P would also be sufficient, but 1P, 2B fit within the power budget, so that was chosen. So that was about PAPI's architecture. Is there any questions so far? If not, we can move on. Oh, there was a question?
I don't have a question, but I want to just correct something here. So FCPIM is not individually optimized for compute bound. It's actually for memory bound.
Yes,
but
yes.
In the memory bound, still we have different arithmetic intensities. So FCPIM is optimized.
Yes. Sorry, yes. Yeah, so even when both kernels are memory bound, that is when we want to send them to PIM, but still FC has a higher arithmetic intensity, so we need a different architecture. Okay, so let us move on to scheduling. So what we want to do is set up a dynamic scheduling. So first, we have to determine whether a given FC is memory bound or compute bound. Then after we determine it, we schedule it accordingly. So how do we determine whether a kernel is memory bound? We have this expression for arithmetic intensity. So it is based on the size of the model. H is some hidden dimension in the structure of the LLM. and it is usually a large number. So you can approximate this to the request level parallelism times the token level parallelism, the batch size times the speculation length. And we see that this formula actually pretty accurately tracks the actual measured arithmetic intensity. So what we really need to do is we need to find a threshold for this RLP times TLP, beyond which we can say that a kernel is compute bound. So this is, I mean, as we saw before, the boundedness actually depended on the arithmetic intensity of the kernel. So and on the parallelism. So even now we know we have a measure of the arithmetic intensity in terms of the parallelism. We use that to compute a threshold, and using that we can decide whether it is memory bound or compute bound. So so first we have to determine this threshold. So we run the fully connected kernels on both the PIM designed for them and the PU, and we vary this RLP and TLP. Then we measure the execution times, and whichever is faster. So if the PU is faster, that means that for this particular configuration, the kernel is compute bound, and if the PIM is faster, it means for this configuration, it is memory bound. And using such empirical studies, we determine alpha. And now once we determine this threshold alpha, suppose we did this and we find that it is 4, let us see how we are going to schedule it dynamically. So first we would we have to first obtain the RLP times TLP, which means we have to obtain the RLP and we have to obtain the TLP. The RLP we obtain by looking at how many tokens are still to be processed. That is the request level parallelism, how many different requests still exist for us to process. And the token level parallelism is usually a system level parameter. So it is just assume that it is written into a register, and we simply read that register to get this number. Then we multiply both numbers, and we compare it against our threshold. So for example, here the RLP is 5, we have 5 tokens, and we read the register and we get TLP as 1. So 5 times 1 is more than 4. So we are in the compute bound region. So we assign it to PU, the processing units. And suppose in the next stage, 1 token disappears. 4 times 1 is still, I mean, it is at the threshold, it is still compute bound. Suppose eventually the RLP decreases to 3, 3 times 1 is less than 4. So now we have to switch to memory bound. So we schedule this to the PIM and so on. Yeah, so that was the scheduling. So we are done with mostly the theoretical part. We just move on to the results now. Any questions so far? Okay, so we can move on to the results. So this the PAPI was compared with 3 state-of-the-art models. The first 2 you see here are essentially GPUs attached with PIMs. The only difference between them is the type of PIM being used. In the first, you have this attack 1 processor per bank PIM, and in the second, you have the high bandwidth memory 1 processor every 2 banks PIMs. And finally, it's also compared with an architecture having only PIMs. So there's an attack only architecture, which does both FCs and attentions and PIMs. And the datasets used were the Dolly creative writing and the Dolly general QA datasets. So in terms of latency, PAPI achieved, so the results were actually similar for the first 2 GPU plus PIM architectures. So the latency speedup of PAPI was approximately 1.8 for both of them. And we do see a very large latency increase for the attack only architecture. Similarly, also for energy efficiency, we see that PAPI improves energy efficiency over the first two by approximately 3.4, and it's 1.15 times more efficient than the purely PIM-based architecture. And we also see that regarding sensitivity to the parallelizations, we see that the attack-only speed up actually decreases with more parallelization, because PIM is not very effective for the fully connected layers that are very parallel. And yeah, similarly, as the token level parallelism increases, it is better. So to summarize, real world LLMs, we have some parallelization techniques in the decode stage, which lead to dynamically changing computer memory boundedness for the fully connected kernels. The contributions of PAPI are first, it introduces fine-grained heterogeneity. So there are processing units optimized individually for the fully connected kernels, when it is memory bound, when it is compute bound, and for the heterogeneous kernels. It introduces, the second contribution is that it introduces a dynamic scheduling framework, which is lightweight and implemented in hardware. And yeah, the result is that it achieves better performance and better energy efficiency than state-of-the-art. So that is all. We can move on to the discussion. So first, the strengths of the paper. I would say the most important strength is that it makes observation that the memory or compute boundedness of kernels can vary dynamically. It produces a system-level solution for this problem. It cuts across like hardware organization and also runtime workload behavior. And it provides a granular approach rather than the one-size-fits-all that we had seen in existing works. And the scheduler is also conceptually simple and lightweight. And the paper produces good comparison with the state-of-the-art. The weaknesses, all the evaluation is completely simulation-based. We will maybe see this in more detail in the discussion. The results are provided for, so PAPI so it brings in two main changes. One is the dynamic scheduling, and the other is the heterogeneity in PIM. And it is not very clear how much of the improvement is due to adding each of these components. They are kind of conflated. There was also an interconnect, which the paper just said was a high bandwidth one, which means we are supposed to probably ignore any overhead due to it. But when we have multiple sort of processors, there may be an overhead due to interconnect, due to condition there. There may also be an energy overhead there. And there are some scalability concerns, which also we will see in the next few slides. So yeah, any questions so far? Okay, so we can move on to discussion one. So here we saw that when the fully connected kernel is compute bound, we send it to the processing unit. And if not, we send it to the PIM. So essentially, if we have for a given kernel, it is being run only in either of these, but we have both hardware already present. So there seems to be some underutilization of hardware here. Could we do better? Do you have any ideas on what we could? Because we have hardware for both the PIM and the processing unit, and we only really need to use one of them at a time. So any ideas on what we could run? Maybe some other, parallelly some other orthogonal function which does not interfere with what we're doing here. Okay. My idea was we could probably run a larger draft LLM in the processor that is anyway sort of fine-tuned for running FCs, although it may not be the best. I mean, it may still be a compute bound, but we could still, I mean, we may get better, we may be able to run a slightly larger draft model, which would improve our speculation accuracy. So that was one idea I had here. Any thoughts on that? Okay, we can probably move on to the next discussion. So we saw that we had to determine this alpha at the beginning using this sort of formula. Any ideas on how we can we do any better here regarding the threshold? So we do have a theoretical computation of the threshold. Yeah.
Oftentimes the data movement bottleneck is dependent on the access itself. Because if you are accessing things in a very irregular fashion, then even though this formula would predict that you will not have any problem with the data movement, you would actually have problem because you are reloading caches for every iteration of access.
True.
So maybe we need to incorporate how the access varies in this formula as well in order to be determined.
True. I had a similar thought. I mean, I had a similar thought of the problem, but my solution was slightly different. So how would you probably incorporate the access into this formula? For example,
there are techniques to write access functions for the memory, like for the memory that you are accessing. So essentially, what you need to do is you need to subtract the first access function for one iteration, let's say I, from a different access function, which is for I plus 1. And then if that difference is beyond the threshold, you would probably guess that, okay, this is going to refill the cache. Now I'm keeping things simple. Let's keep it like one-dimensional.
Okay.
We can actually incorporate more math to make it more. All of this is like part of polyhedral analysis, which in itself is quite detailed.
Okay.
That would how I would do it.
Yeah, makes sense. That is also, I mean, that would work. What I was thinking was we could update the threshold also live using maybe some reinforcement learning or some online technique. So yeah, I think that will also take care of this in a more automated. I mean, where we wouldn't really understand what's going on, but maybe we would get better results overall if we. Yeah. Any thoughts on that?
I think the RM model will also eventually actually model that equation that we would get.
Right. Exactly.
But it would require some training and.
Exactly. Yeah. I mean, we wouldn't really understand what's going on, but I think the final model we get would be very similar. Yeah. Yeah. Any other thoughts? Yes.
We're running the smaller one at the same time, right?
Yes. That's sorry. Do you mean in the previous discussion or in general?
No, in general.
In general, we are running a smaller model.
And this factor could be different for both models, right?
The hedge, you mean?
The alpha factor could be different for the large model that we're trying to divide in both processors, and the smaller model which we use to predict the ground. Right?
True. Yes, the alpha could be different, but I mean, my idea was simply just run the smaller model on this only when you're not. What we really want to optimize is the larger model. The smaller model is just a helper. So it is, I mean, instead of wasting the unutilized hardware that we have anyway built, we could as well run something on it, like a larger version of the small model. So yeah, we don't need to optimize the smaller model for alpha, etc. for this. Thank you. Any other suggestions, thoughts? Okay, if not, we can probably go to the next discussion point. So about scalability, like I mentioned earlier, so if we have a lot of PIMs and processing units and maybe multiple CPU sort of system that is interacting, so what do you see any concerns with what we have seen so far, what the paper has discussed, and any thoughts on what could go wrong, or will it what is already discussed here?
Well, the larger or the more processes essentially that we have, the larger the distances between the processes become. So we need more time to take the data between them. Even though we're doing most of the computing in one processor, then we still need to give it back to some other processor that does the next stage.
True. That is certainly an issue, but also when you just have a lot of different things that are interacting with each other, do you see any other issues also?
There's a heat at the bottom of this slide.
Yeah. So yeah, essentially coherence may be a problem, and the paper does not discuss coherence in any detail at all. So yeah, any ideas on how we could solve this? What could be done to alleviate this? I also don't have any great ideas. It is just lazy PIM has. There are some works on how to maintain hardware coherence for PIMs and between PIMs and processors. So yeah. So that is what. So just to summarize, we saw three main areas of improvement. So we could alleviate the underutilization that we get, because we are specializing for two different modes of the same kernel, so to speak. So we have anyway built the hardware, might as well use it for something else. The threshold may not be completely captured by just the arithmetic intensity. There may be some other factors which we can also capture dynamically. And for scalability, we have to think about coherence and solve it using maybe some existing works that may help here. So that is all. Thank you. And also thank you to Harshita and Xiaohen. Sorry if I'm Sheehan. So yes, for helping me with the slides and for all the feedback, etc. Thank you.
So thanks a lot. I think it was a good talk. I didn't like some of the weaknesses you mentioned, specifically the first one regarding simulation-based technique. So my question is that what else you can do when you want to change the hardware? So is there any other way you can evaluate your idea? So we have two options: don't do research, or essentially use some simulation infrastructure to evaluate the idea, because this is a very important. Simulation is actually very much important, that since it enables a lot of study, a lot of, let's say, future study, which is going to be very important. So
makes sense. Okay.
That's the one. And also regarding the correct that's a mistake that you had in some of your slides regarding FCP.
Yes.
It would be great if you update your slide and send the updated version to Japan, and they can update it on the website. But other than that, I like the discussion points. Actually, I think it was really good. Jihan, do you have something to come?
Yes. So the good point of this work, I would say, is to enlarge the design space of the architecture, incorporates more designs, components, it includes the GPU and more processing memory at different granularities. This is a good point of this work. But the bad point of this work is it just enlarged the space and did not have a detailed exploration of this space. So I would say this is also a good thing for us, because I have more research on how to design a a smart heterogeneous system. So I think for we have emerging AI models more like MOE, some diffusions, visual large language models, something, and how we use this hardware to support those emerging models. So this is the thing we need to think about. And yes, thank you.
Okay, great. So yeah, with that, I think we conclude today's session. Don't forget to attend the quiz. It's already released, or
It will be released in 20 minutes because it ran a bit late for today.
yeah. So yeah, you have 1 day to basically solve it. And also another reminder, please make sure you contact your mentors soon enough, because not all mentors are, friendly enough to provide last-minute comments like this. So make sure that you contact them soon enough and have at least 2 meetings with your mentors. Thank you so much.
Thank you.